Hello, and welcome to the Blue Waters webinar series. This is Maxim Belkin with the Blue Waters project at the National Center for Supercomputing Applications at the University of Illinois. It is my pleasure to welcome you today to a new session in the Scientific Visualization webinar track. Today's webinar is titled 3D Scientific Visualization with Blender and will be presented by Brian Kent, a scientist with the National Radio Astronomy Observatory in Charlottesville, Virginia. Brian earned his PhD in astronomy and space sciences from Cornell University. Currently, he studies the dynamics of galaxies in the universe at radio frequencies, but as you could already guess, he's also interested in 3D scientific visualization. Before we begin, I'd like to remind everyone that you can post your questions through the YouTube live chat and through the Slack channel. Information on how to join our Slack can be found in the sidebar. With that, thank you all for joining us today, and thank you, Brian, and I'll turn it over to you.
Thank you very much, Maxim, and I appreciate my colleagues at NCSA and Blue Waters for hosting this webinar and the invitation and the opportunity to speak to everyone today. So hello, everyone. As Maxim said, my name is Brian Kent. I work at NRAO in Charlottesville, Virginia, and today I'm going to talk to you a little bit about 3D scientific visualization, some of the things that I'm interested in working with in terms of 3D graphics and different kinds of astronomical data. So we're going to go through some slides here and give an overview of what I work on, the kinds of things that I'm interested in, and then we'll do a live demonstration and a brief tutorial in terms of how you actually manipulate some of your data with 3D graphics. So we'll go ahead and get started. And as Maxim said, please ask any questions as we go through the online seminar. So an overview of what I'll be talking about today is, first off, the science domain and data types that we work in with astronomy. And while astronomy has its uniqueness in terms of what it studies and how we acquire data, once the data are acquired, it's no different than images and data cubes and simulations that you have in other scientific fields. And so I hope that a lot of what I will talk about, while it is obviously skewed towards what I work with in astronomy and astrophysics, you'll clearly see is applicable in other scientific fields as well. I want to kind of briefly touch on why we need to visualize data in the first place. What is our motivation for doing this type of scientific computing and how it helps us out. The specific tool that I will be discussing is an open source tool called Blender. It's wonderful for scientific visualization, so I'll be giving some examples how I use it and the different kinds of data that you can visualize with it. And then I'll give an introduction to using its interface. There are many wonderful tutorials on Blender on the web and on YouTube, so I'd encourage any of our listeners to check those out if they see something during my presentation that they think they might be able to visualize, and if they want to actually get started with the software. So I work at NRAO. This stands for the National Radio Astronomy Observatory. Through the National Science Foundation and under cooperative agreement with them and our parent company, Associated Universities Incorporated, AUI, we operate radio telescopes all over the world. And you can see some of those here. We have the Green Bank Radio Telescope there on the left in the mountains of West Virginia. We have the ALMA telescope, the Atacama Large Millimeter Array, which is located in Chile in South America and is a joint venture with our colleagues all over the world, including Europe and Japan. We have radio telescopes that extend all the way across the United States, called the VLBA, the Very Long Baseline Array. These telescopes are comprised of a 12-element interferometer extending all the way from the Virgin Islands to the island of Hawaii and all across the continental United States for doing high resolution imaging. And then finally in New Mexico, we have the VLA, the Very Large Array, which is a 27 element interferometer. You can see a picture of the telescope here at sunrise. And well, these telescopes are all used in concert by scientists to study astronomical phenomena at radio wavelengths. And there's all kinds of different astronomical phenomena that we can consider, and some of these I'll be talking about today. We have solar physics, extragalactic astronomy, studying nebula in our own galaxy, studying planets in our own solar system, cosmology, extreme gravitation, pulsars, astrochemistry. There's a whole host of different kinds of phenomena in the universe that you can study with radio telescopes in addition to telescopes at other wavelengths. But at NRAO, we're focused on the radio part of the spectrum that you see here on the left-hand side of the diagram, extending all the way from the low frequency end of the electromagnetic spectrum up into the high frequency, into the several hundred gigahertz area, where we have to kind of navigate around the absorption of radio wavelengths due to water, and that's one of the reasons why we put our radio telescopes at very, very high altitude in order to get above some of that water vapor absorption. But one of the reasons that we cover such a wide area of the electromagnetic spectrum is because there are different phenomena at different radio frequencies. And I'll show you some examples today of those different phenomena and why we're interested in the astrophysics of said objects. So here's an example. This is the Whirlpool galaxy, Messier 51, and what it looks like across the entire electromagnetic spectrum, including X-ray, where you're going to see the high energy emission, the UV, the optical, the near and mid-infrared, the radio continuum, and then on the right-hand side you see a beautiful optical picture. And then in the orange and the blue, right there in the center and on the right-hand side, you see the 21 centimeter, the 1420 megahertz radio emission of neutral hydrogen. And as you can see, which is color-coded in blue right there in the middle, that this hydrogen gas extends well beyond the disk of the galaxy. And this is a view of the universe that we would never have if we didn't have radio telescopes. And one of the neat things is that we can actually create a Doppler shifted data cube of that hydrogen and other chemical elements as well, and visualize it in 3D. And that's something that we'll look at towards the end of the seminar. Here's a view of the multi-wavelength Milky Way as produced by NASA, again showing what our own Milky Way galaxy looks like from the radio continuum at the low frequency of 408 megahertz. We'll come back to that near the end of the talk as well. Neutral hydrogen, molecular hydrogen, the infrared, the dust emission that we see with infrared telescopes, and then going all the way up to the high energy X-ray and gamma ray emission. So depending on what kind of wavelength and frequency you look at and what kind of telescope you're using, you're going to see a different view of phenomena in the universe. But what I typically focus on is observational astronomy. So astronomy and astrophysics is unique in that almost everything that we do is remote sensing. So we don't perform experiments typically in a laboratory like a chemist or a geologist or a biologist would. Everything we have to do in terms of acquiring our data has to do with remote data acquisition. So whether you're using an optical telescope like the Palomar telescope in California, or the Green Bank telescope, the Hubble Space Telescope in orbit, or the Very Large Array in New Mexico, you're going to be getting your photons have a long way to travel across the universe before you acquire them. The exception, of course, in astronomy is planetary exploration, where we can actually send probes and rovers to planets like Mars and acquire data directly that way. So it's unique in that we actually can't physically reach the objects that we want to study, but it's actually a little bit of a forte in terms of our astrophysical sciences, in that the entire universe becomes our laboratory. And astronomy is wonderful because it's really all about extreme physics. We have some of the most extreme environments in the universe, and we can study those with our telescopes. We can either do broadband continuum emission studies with our radio telescopes, or we can study spectroscopy. And spectroscopy allows us, by breaking the electromagnetic radiation into its constituent components, its colors, if you will, as an analogy, you can study the dynamics and the kinematics of galaxies, but you can also do astrophysical chemistry and study the building blocks of compounds in all kinds of different objects. So we're also interested in looking at the time domain in astronomy in terms of looking at, Earth crossing asteroids. There are a lot of studies now where we're actually looking at light curves and finding extrasolar planets. We do pulsar timing, which alludes to what I mentioned before, the extreme physics, but also comparing epochs of data years apart and looking for those really, really interesting objects that we might not have been able to find before if we didn't do time series studies. But we're not limited in astronomy to doing just observations. We can also simulate with different kinds of studies like n-body simulation, smooth particle hydrodynamics, and I have some examples here of where I'm crashing two galaxies together. We'll look at that example a little bit later. And then also looking at interacting binary stars. And all of these are interesting because they beg to be visualized with three-dimensional graphics. And so that's one of the reasons why I'm going to use those as examples in some of our tutorials. So why is it that we want to visualize our data in 3 dimensions in the first place? Well, let's consider some of the telescopes that we operate here at NRAO. Telescopes like the Atacama Large Millimeter and Submillimeter Array in Chile. 2014, we looked at 1,300 terabytes of raw data. 2,700 terabytes of data in 2016. Our telescopes in New Mexico, the Very Large Array that you see here in the photograph, can actually produce a million simultaneous frequency channels. And the project that you see in the lower panel there are images of distant radio galaxies that we've collected with the VLA Sky Survey. The VLA Sky Survey, or VLAS as it's known, it generates 300 gigabytes of raw data in just 4 hours, and that's before the data has been calibrated and imaged. And the reason that we're interested in pursuing these very high data acquisition rate projects, you can see here in this panel. This is an optical image on the left-hand side. The middle is what the VLA was able to observe 20, 25 years ago in terms of its most compact configuration at 1400 megahertz. And the right-hand side shows you the state of the art with the VLA Sky Survey that started in September 2017. And you can see we get exquisite resolution and detail. And the VLA Sky Survey will actually be cataloging 10 million objects at high resolution, like what you see on the right-hand panel. And the nice thing about this survey, and why I like to mention it in a visualization seminar like this, is that this is a survey that is actually produced by the observatory in collaboration with many universities as an open project. Within days of the data actually being taken, all of the images are available for the public to use and do science studies. Anyone who wants to look at it can actually do that. So I encourage our listeners to check out our VLA Sky Survey project and take a look at some of our imaging projects and products. But this shows, this graph here I always like to show because it kind of gives you a 25-year review leading up to where we're going in terms of data acquisition and why archives and pipelines and visualizations are so important in astronomy. 25 years ago, our NRAO VLA Sky Survey that was done in the most compact configuration at 1400 megahertz, the data set took up about 50 gigabytes of space. Okay, that's relatively small by today's standards. And as you can see, we continue to trend up on this logarithmic scale, going through projects like 2MASS, GALEX, the Alfalfa Survey at Arecibo, where the Hubble Space Telescope was in 2014. And then in blue, you see current projects, some of which I'm involved in, including VLAS, but the current state of the ALMA archive, pulsar projects. We're getting up into the to the petabyte and exabyte ranges, looking towards the future in yellow there of the Large Synoptic Survey Telescope and the Square Kilometer Array. So we have to have very, very creative ways of being able to manipulate, calibrate, image, and visualize our data. And in the future, the NRAO is planning on building several hundred radio telescopes in the southwestern United States in a project called the Next Generation Very Large Array. So NGVLA will push the boundaries of data acquisition, calibration, data management, and data visualization. So it's a very exciting project that we're working on here at NRAO. So we're not limited to just one specific kind of data in astronomy and astrophysics. It depends on what kind of science you're trying to do. You might be looking at a data cube like you see in black there on the left-hand side. This is a cosmological simulation showing the large-scale structure of galaxies in the universe. You might have three-color images, such as those taken with the Hubble Space Telescope. So you see the Orion Nebula there in the lower left-hand corner. But you might have three-dimensional catalogs like the Hipparcos Parallax Survey you see there on the right-hand side, or you might have orbital imaging of planets like Mars, as you see in the lower panel. So depending on what kind of astronomy and astrophysics you're actually interested in studying, you're going to have different kinds of data. Why do we need to visualize this? Well, it all goes back to not only the increasing data rates that I showed a couple of slides ago, but also the fact that the data are constantly becoming increasingly complex. So in the left-hand panel, I have a single spectrum of a single galaxy, IC10, where we measure a single spectral line. Okay, we learned something from this. This was data taken back in the 1960s. This was state of the art back then, where this spectrum of a single galaxy was actually relatively difficult to obtain, but told us a lot about that single galaxy. But instead of studying a single spectral line now, we've now moved to the right-hand panel, where we have dozens of lines in a very, very relatively small bandwidth, taken with the ALMA telescope in Chile, where we see dozens and dozens and dozens of chemicals and different spectral lines that we have to work to identify, some of which are not known, and scientists have to work on actually studying these. So we're moving from a single spectral line to hundreds of spectral lines, and in the same idea, we're moving from a paradigm of studying a single galaxy to now mapping millions of galaxies with our surveys. So in addition to this taking up enormous amounts of hard drive space, we have to have efficient database usage. We have to be very creative with our signal extraction methods because a single person can no longer do that. And we need to have efficient and creative three-dimensional visualization techniques using software that may not typically be used in the scientific community or in my particular field in astronomy. But we can also take advantage of high performance computing. And as I'm sure many members of our audience listening today are familiar with, using GPUs is advantageous for speeding up your rendering. So this graph on the right-hand side shows a histogram of what you get typically with a CPU there in the dashed red line. But if you use something like NVIDIA CUDA or OpenCL, you can actually greatly increase your rendering time by a factor, in this case, a factor of 4, just by turning on those plugins and using the advantages of GPU computing. So that's another way to kind of increase the efficiency and decrease the time of your data visualization, which is one of the reasons why I like using the Blender tool. So Blender is not unique in terms of 3D graphics rendering and visualization capabilities. There are many wonderful products, including Autodesk Maya and 3D Studio Max, Lightwave, Houdini, Cinema 4D, and as a rendering engine, Pixar's RenderMan. But one of the reasons that I like to use Blender is because it is an open source project, and you're able to script it in Python. And Python is an incredibly popular language in astronomy, and so anything that is Python based is usually very attractive to astronomers in terms of wanting to reduce, analyze, and visualize their data. So what exactly is Blender? Well, you can go to blender.org and download it and read all about it. They just came out with their latest beta for version 2.8 with a bunch of wonderful new features. 2.79 is the current stable release, and it's actually what I will be using for my demonstrations. But it's 3D graphics software. You can use it to model, animate, and visualize. It's used by the entertainment industry for pre-visualization. It's open source. It has a real-time 3D viewer and a wonderful GUI interface that I'll be showing and demonstrating. And as I mentioned before, you can use Python in its scriptable interface for actually loading your scientific data. So if you can use Python, you can use Blender. So we have to consider when we're doing our scientific visualization, how are we going to build what is going to be our workflow? Well, first we have to start with some sort of either physical model or a container for our actual data. Is this going to be a three-dimensional data set? Are we going to apply two-dimensional textures to it? How are we going to project that data and the textures onto said models and objects? We have to consider our lighting. How are we going to illuminate the data? Is it something physical that highlights something in a simulation or a data cube? Or is it some sort of artistic choice that allows us to better see the said data? How are we going to move our model around? How are we going to control the camera? What kind of lens selection are we going to have? Are we going to have multiple cameras? Are we going to track something during a simulation? And then how are we going to put it all together? And this deals with the compositing and finally the rendering. Are we going to create a video? Is it going to be a static image for a publication? How are we going to layer all of the final output and create the final products? So this is a kind of a visual flow chart of what I just mentioned. We're going to have our data visualization scene that eventually is going to become our rendering layers. We can have things like environmental lighting or what's called ambient occlusion in our backgrounds. And those are what I would classify as our world parameters that are going to be sitting within our scene. And then we're going to have our models, our lighting, our cameras, our animation, each of which are going to produce different objects and different layers within our data visualizations. And within each of those, we're going to have different things like surface textures and modifiers that might increase or might decrease our rendering time, increase our efficiency in terms of how efficient we want to make our data visualization. We don't want this to take forever in terms of rendering, so we can be creative in how we actually build our models, how we deal with our lighting. Do we want something? There are trade-offs like ray tracing and diffusion that might make our data visualization a little bit more aesthetic and appealing at the cost of making it make the rendering time take a lot longer. And how do we want to deal with our camera setup? Do we want a telephoto shot? Do we want it to be wide angle? Do we want an orthographic or a perspective view? How do we place constraints on our camera? That's something that we'll go over very briefly in our tutorial. And then how are we going to animate all this together? Are we going to be moving our cameras? How do we leverage Blender to actually insert the keyframes and do what we call graph editing to actually move all of these objects around together in concert? Then we combine all of these rendering layers and we either export a still frame or a high-resolution video. Some of the examples I'll mention at the end, where we're doing kind of augmented reality style of visualization, we can actually render things at beyond 4K. We can even do an 8K rendering, so that way we can see all of the detail and import the videos into YouTube to take advantage of the YouTube augmented reality tools. So we can start with very, very simple models, cylinders, cubes, cones, spheres. We've got an icosahedron, a torus there, and this looks relatively simple, but when it comes down to your rendering time, if things are very, very far away from your camera view, it might be advantageous as a user to pick something that has fewer polygons, fewer vertices with it, that may not have faces on it, because that will greatly decrease your rendering time. So you have to be very careful in terms of how you actually choose your models. Once we have our model, in the case of doing a planetary mapping, we can take examples like data from NASA and planet Earth and actually map those projections onto a sphere. Once we have that, we can actually animate our data. This is a graph view of the animation, and you can tell from the sine curves here, we're actually doing a rotating camera view where we've got our location, our rotation, and our scaling. In this case, our rotation moving together in concert, and I can actually click and drag on each of these graph elements to change the animation and then re-render my data visualization. So this is a wonderful tool for being able to precisely control the movement of the objects in your data visualization. We can take into account, as I said before, our camera control. So in this case, I have 3 cameras pointed at my Earth visualization. One camera on the left-hand side is actually moving in orbit of the planet, of my planet Earth, in my data visualization. And it actually stays pointed at planet Earth. The other 2 cameras are static. The one on the right-hand side is currently selected, and I can move these in any way I want within my data visualization scene. I also have to take into account my rendering engine. Blender has 2 included rendering engines. It'll have a new one in version 2.8, but the ones that are included with the demo that I'll do today are called Blender and Cycles. Cycles is nice because it allows you to do a real-time rendering, which is great for scientific visualization. But there are also third-party data visualization rendering engines, including YAF-Array, LuxRender, and Octane, as well as Pixar's RenderMan, which is wonderful as a choice because it allows you, it now has a plugin for Blender, so you can actually plug into RenderMan and use it as well. And one of the features that I really, really like about Blender is its node compositor feature. So compositing in this sense actually allows you to do object-oriented programming in a visual sense. So I build this graph here that you see on the screen with a number of different node elements representing different elements of my data visualization. I've got my rendering layers, I've got curve adjustments. Some of these are kind of for an aesthetic purpose, but what I do is I stitch these lines going from the output of one element to the input of the next element. And I connect all of these together into my final rendering element here on the right-hand side. So what this allows me to do is visually prototype my data visualization scene without writing any code whatsoever. But as you'll see in the interface, if I hover over any of the elements in the Blender interface, its Python API will give me a pop-up and allow me to put any of those elements into a Python script. So what this allows you to do is it gives the user very rapid prototyping in terms of building a data visualization scene. So it's a really, really nice feature of the software. So putting all of this together, going from panels A through F, I start with a spherical wireframe mesh. I project onto it actual data from a Mars orbiter. I add lighting elements that is based on the actual ephemeris from where the sun would be on a given day and time. I can animate said lighting element representing the sun in panel D. I can move my camera around an orbit in panel E, and then I have a final data visualization that you see in panel F and also here that I can create in Blender as the sun peaks over the edge of the planet Mars there. And this is all done with actual data. So let's look at a couple of examples. So planetary models. These can be high-resolution maps that are typically from satellites, but I also want to add in things like atmospheres, backgrounds, and different lighting elements to create a very realistic presentation. So there's a wonderful video tutorial on how to do these kinds of things on the website Blender Guru. This is how we do it with a nighttime and daytime view, as you'll see on the next panel, view of the planet Earth. And this is what we actually get. In this case, I'm doing a zoom in to our telescope facilities in Chile. But this element it's not just this visualization has elements that comprise not only day and nighttime imaging in high resolution, but also clouds and atmosphere to create a realistic presentation of what the Earth looks like. And I can animate this. I can change the terminator as it moves from day to night and actually create a realistic visualization of what planet Earth looks like. In terms of kind of extreme astrophysics, we study with radio telescopes objects called pulsars, which are rapidly rotating neutron stars. And by rapidly rotating, there's a category of pulsars called millisecond pulsars, which rotate 1,000 times per second, if you can imagine something moving that quickly out in space. But these dead stars have extreme magnetic fields, and so one of the things I wanted to do was actually build a three-dimensional model of those magnetic fields around the pulsar. And the pulsar is the very tiny dot that you see at the middle of the graphic. But then I'm actually showing the magnetosphere in 3 dimensions surrounding this neutron star object, this pulsar. We're also interested in studying data cubes, and so data cubes, as you see in the lower part of this slide, can come from cosmological simulations of large-scale structure, or they can come from radio telescopes. And with radio telescopes, we can produce gridded data over 3 dimensions that cover 2 coordinates on the sky. These are our X and Y positions, what we would call right ascension and declination. But the 3rd dimension is actually the Doppler shifted velocity and frequency. And using these 3 coordinates, we can actually study the dynamics of galaxies. We can look at planetary disks, and as I said before, the large-scale structure and the formation of galaxy clusters. So in terms of studying data cubes from galaxies in the nearby universe, we can actually build a density map based on galaxy surveys. So the results of those surveys, whether they be from redshift surveys of optical telescopes or what we call neutral hydrogen surveys with radio telescopes, we can not only look at the density of galaxies in 3 dimensions, but also the effects of gravity and build a flow model map in those regions of space. So the animation that's hopefully playing on your screen right now is data from the Point Source Redshift Survey Catalog project. And on the left-hand side, you see the density map of galaxies in low resolution. And on the right-hand side, you see the influence of those galaxies. And this is a nice way of looking at the catalog of galaxies in 3 dimensions. But those are some relatively straightforward examples of observational astronomy and what we get after we map the positions and the redshifts and the distances of tens of thousands of galaxies. But as I mentioned at the beginning of the talk, we can also do astrophysical simulations. So there's a wonderful package called Gadget 2, which stands for Galaxies and Dark Matter Interacting. This is an n-body and spherical hydrodynamic code that you can download there at the link. And so I can do cosmological simulations, or I can do n-body simulations where I crash 2 Milky Way-like galaxies together. So if I take 30,000 particles in each galaxy, I let it run for a simulated time range of 2 billion years. Well, then I know how to read in those snapshots with Python. So therefore, I can use Blender to actually bring those XYZ positions for each snapshot into vertex measurements of a Blender object, texture them with halos, and then on a grid here actually move my camera around, and we'll look at this in detail here in a little bit, and actually play out my simulation that I've created with Gadget. So really a wonderful tool for doing n-body simulation rendering. Also, in terms of 3D, I can take the what's called the extragalactic distance database. There's a citation there at the bottom of the page, and actually map out several thousand galaxies in the nearby universe and look and see what those actually look like in 3D. But we're not limited to astronomy. we can also take a look at other sciences. And so I would point all of our viewers listening today to BioBlender, which is a great biochemistry project that uses Blender to do renderings of molecules in 3D. And they've actually have built their own interface to do the analysis and the rendering. So definitely check out their project. And also with geographic information systems and geography and GIS, Blender has been used to actually map out urban areas like you see in the graphic here. So there's a wide range of different different topics and different sciences that I think Blender is advantageous to actually use in. And one of the things that I've been working on recently is actually using Blender to project and remap all sky maps at different wavelengths and frequencies, and combining that with the Google Spatial Media Module, which comes both as Python code and as a standalone built binary, to actually use the data viewer that everyone has in their hands all the time, which is either your tablet or your phone. So the Google Spatial Media Module allows you to exercise the accelerometer in your phone or tablet and actually view the night sky at different wavelengths. And I have some examples of this on my YouTube channel. So as you pan your camera or your phone and your or tablet around, or it'll also work in your desktop browser, Firefox, Chrome, all of the major browsers are supported. You can actually look at the sky and see what it would look like at 400 megahertz, see what it would look like in the infrared at 1400 megahertz. And I've actually published a paper on this. It's available on the IOP Science website, so I'd encourage our listeners to actually take a look and see the tutorial of how you actually build your own 360-degree spherical panorama of your all-sky data. But we're not limited to just using all sky maps, which is a flat projection and two-dimensional in nature as we pan the camera around. But we can also actually do it with the extragalactic distance database. So if you look at this example on YouTube, this basically takes you on a simulated ride through the nearby universe, but as the video plays using the Google Spatial Media Module, you can pan your phone, tablet, or desktop browser around and look at the galaxies as they pass you by. So it allows it's a really nice education and public outreach tool, but it's also nice for research scientists because it allows you to get a better view on what your data actually look like in 3 dimensions. And I also want to mention some of my colleagues here around the world who are also working on 3-dimensional visualization, including Chris Fluke here on the left-hand side and Danny Vole, who recently completed his PhD. Here they're using Oculus Rift and a cave facility to actually do 3-dimensional data visualizations of data cubes. So I would definitely check out their work. They're doing some wonderful things with their different kinds of galaxy surveys and science. Also, there's a wonderful package by one of my colleagues, Jill Naiman. She's written something called AstroBlend, which uses Blender to do 3-dimensional visualization. Also, Reese Taylor, who specifically studies neutral hydrogen in nearby galaxies, and he has tailored the Blender interface for specifically doing neutral hydrogen astronomy, and has done a wonderful job with studying galaxies and his tool there. And also grad student Matias Garate in Chile. He has done simulations of protoplanetary disks and stellar winds, and all of the data that he has created with his simulations, he has actually run through Blender to do 3-dimensional visualization. But Blender also has some wonderful tools in terms of broadening participation and education and public outreach. So I'd like to mention a couple of colleagues here and their papers. We have Benedict Deemer and Isaac Fazio here on the left-hand side. They are actually doing large-scale studies of the universe by using Blender and leveraging that for 3D printing. Thomas Madura is doing something very similar with Ada Carina. and actually building three-dimensional models using Blender and 3D printers um, for those who are visually impaired. So it's broadening the participation and bringing astronomy to everyone using Blender and a nice combination with 3D printers. And here at NRAO, we have our own exchange and outreach program called NINE for students. This stands for the National and International Non-Traditional Exchange Program. And our students there are interested in using data from our telescopes and all kinds of different visualization tools to accomplish that. And finally, I'm reaching the end of my slides here. I want to mention the publications of the Astronomical Society of the Pacific. We've published a special focus issue on data visualization in astronomy, specifically focusing on techniques, methods, and tutorials. We would like to produce a second data visualization issue through PASP. So if any of our listeners out there in astronomy and related fields would like to be part of that special focus issue, please contact me, and I'd be happy to get us and get any interested parties in touch with the editors to actually contribute to our second volume. Our first volume was successful, and we're anxious to look for a second volume here in the future. So with that as an introduction.
Brian, may I interrupt you?
Go ahead. Please do.
We had one question.
Okay.
I'll ask the question, and then you may want to generalize the answer. The question was, does your university offer an MS in this field? I might modify it to say, how did you learn your background experience to relate to that question?
Oh, that's a great question, and as you've probably guessed, this is not a traditional tool that was designed for science, but because of the question that was asked is how did you learn and get into these things, is there's a wonderful conference that is held by ACM, Association of Computing Machinery, called SIGGRAPH, which stands for Special Interest Group in Graphics. And typically the conference is either in Los Angeles or in Vancouver. But that I gave a talk there, and it afforded me the opportunity to speak with a lot of people who are not necessarily in astronomy, but have a background in computing, in physics, and they understand three dimensions. They understand 3D graphics. They understand visualization. And so I was able to learn a lot by attending a conference like that, and really learn from the experts. And Blender has a presence there at the conference every year, and really learn from them and learn how to do three-dimensional visualization and then apply it to my own data in astronomy. And Blender, the Blender Foundation has a great YouTube channel. Check out their website. It's blender.org, and they've got lots of tutorials. And I think you'll quickly see, okay, well, maybe I can adapt what they're doing for an animation process or some sort of building of a 3D model into your own data. So that's a great question.
We have another question.
Sure.
What are the major differences between Blender and other scientific visualization tools such as Vapor, Visit, ParaView, etc.?
Right. So the difference with Blender, I think, is well, it's open source, and most scientific tools are going to be open source. But I really like that Blender is multi-platform. It works equally well in Windows, Mac OS, and many flavors of Linux, and I use it on all three. The interface does not change between any operating system. It has a Python API, as you'll see very, very shortly. So if you can write Python code, you can use Blender, and it's open source. So compared to other tools that are popular in the graphics industry, the price is right. It's under active development. It has a large community of developers who are interested in adding features to it. And I think for some of the data visualization tools that our questioner mentioned there, those are typically built for, they're wonderful tools, but they're typically built for a relatively specific purpose or range of purposes, but Blender tends to be a little bit of a Swiss Army knife in that you can use it to your advantage for all different kinds of data visualization examples. So those are some of the reasons why I like it.
No other questions at this point. Thank you.
Okay, thanks very much. So we'll take a break there from our examples and go through a brief tour of the Blender interface and then hop on into an actual session, and I'll kind of show you around what the interface looks like and some of the different kinds of things we can do with it. So this is what a typical
Excuse me
Blender
again.
data visualization.
If I may, another question.
Yes, another question. Go ahead, please.
For your animations where you're driving Blender with simulation data, have you identified methods that make that faster for large vertex models? I've mainly found the for each get, for each set methods.
Yes. And so what you're actually seeing on the screen right here is a galaxy, and I've kind of increased the size of the points so they show up on the slide. But one of the things that you can do is actually create a single object with many, many, many vertices. And Blender considers that to be just one object, and it renders much, much faster. And there are a number, I don't know if the question came in from Slack or YouTube, but I did post on YouTube a link to my tutorial website, and I actually have one of my n-body simulations on there, and it has hundreds of thousands of points on it. But I can actually render it relatively quickly. It doesn't bog down the interface or anything like that. I also have a tutorial book that I'll mention at the very end of our seminar here, and a number of very, very creative graduate students have actually sent in examples that they've done, and if the listener or the listener and individual who asked the question wants to contact me, I can actually send them some methods for doing said n-body simulations with high numbers of points. Absolutely, absolutely.
Thank you.
Thank you very much. I appreciate the questions. So this is what the interface actually looks like. The main viewer is going to be here right in the middle of our screen. We have our object tools in panel A on the left-hand side. We have our transformation tools for positioning things in panel C. We have our viewer and overview of all the objects that are in said visualization in panel D. Panel E is our properties controller. And then panel F is our tape deck player, if you will, even though people don't really use tape decks anymore. It allows us to fast forward, rewind, and play our visualization. It's basically the time element, the time series of how our data visualization is going to play out. And one of the basic things that we actually want to be able to do in the interface is translate, rotate, and scale our objects that are in our 3D viewer. So that's what this is showing here, and depending on whether you're translating, rotating, or scaling, the three-dimensional mouse pointer is going to change along the X, Y, and Z axis, depending on how you're actually going to do your manipulation. So I'll come back to this final slide here at the end of our seminar, but for now, I'm going to exit my slides, and I'm going to move into a Blender session. And that should be broadcasting on everybody's screen. And when you start Blender, this is what you're going to see by default as it comes up. And as people are following along on YouTube, I actually have a screencaster recording my key inputs. So as I move my mouse here in the lower left-hand corner and hit different key combinations, you should be able to see what I'm doing either live or later on in the replay if you want to revisit something that I'm actually doing. So what I can do here is I can use my middle mouse wheel to zoom in and out. I just have a simple cube. That's the default object that comes up in the Blender interface. But I also have two other objects. And I select any object, which is always going to be highlighted in orange, with my right mouse button. So first I'm going to select my camera. It highlights in orange. I'm going to go back to my cube. It highlights in orange. And then I'm going to go to my single lighting element. Also right-clicking, highlighted in orange. The crosshairs that are right now located in the middle of the screen is my three-dimensional cursor. This allows me to place any three-dimensional object at the location of the cursor. So if I move this cursor with my left mouse button over here, or down here, and then hit Shift A, I can add a different object called a mesh. And this gives me my basic mesh object primitives: a cylinder, a cone, a torus. I'm going to add a sphere. And it puts a sphere right where my three-dimensional cursor was. If I want to move the object, I grab it with the G key, and then I can move it anywhere in my three-dimensional viewing space. If I want to grab and move it and constrain it to a single axis, either X, Y, and Z, I can do G and then X, and you'll see a red line. Red is always X, and now it's constrained to move along the X-axis. If I want to do the Y or Z axis, I can do G for grab, Y, and move it along that axis. Same thing for Z, up and down. And I'm going to go back and right-click and click, select the cube. I can do, those were translating motions of a three-dimensional object. If I want to rotate it, I can do it along the X, Y, or Z axis. So I hit the R key, R for rotate, X, and rotate it about the X axis. If I want to rotate it about Y, R and Y. If I want to do Z, R and Z. If I want to scale the object where it sits, I hit the S key. And I can increase and decrease the size. If I want to stretch it and scale along a certain axis, I can hit S and X, S and Y, or S and Z. Now, for a scientific visualization, I might start out prototyping something like this, but I'm eventually going to want to prototype exactly where it's going to be. So I can click on this tiny little plus sign on the right-hand side and do a transformation, either moving it along the X-axis, the Y-axis, or the Z-axis, and I can do the same thing with my rotation and my scaling and changing the dimensions of my object. I can slide this out of the way here. And if I zoom into my cube and I want to manipulate the vertices of said object, I can hit the Tab key and move from object mode here in the lower part of my screen on the left-hand side, hit the Tab key, and move into edit mode. So now the entire object is actually highlighted, and I can right-click to select any vertice and hit the G key and move it. If I want to constrain it to the X-axis, I can hit the X key. And in this way, I can deform and change and manipulate not only the object, but the constituent components of said object in any way that I want. And going back to the object panel up here, one of the nice features that I mentioned in my slides of Blender is that I can position things very, very precisely exactly where I want them to go, which is what you would want to do with an astrophysical simulation. So if I hit the Tab key and go back to object mode, if I hover over any of these panels, it tells me here location of object, Python object.location, and then in the Blender Python module, so if you've written any Python code, at the preamble of my script, I'm going to do import BPY. This tells me what the API is. It's bpy.data.objects, and then access the element cube, and then I can set the location for either X, Y, or Z, And that location is just a 3-element list. So I've got index 0, 1, and 2. And that will allow me to manipulate the position within a Python script. And if I don't know where that is in the API, all I have to do is hover over the element and Blender will tell me what it is. It's really wonderful software in terms of discovery of how the GUI and how the interface actually works. So
We have another question, if you don't mind.
yes, please go ahead.
So the question is, I'm a Houdini artist. Where can I get data and tutorials for the astrophysical simulations? That's probably a useful question for the audience in general, though.
So can you repeat that question one more time?
I'm a Houdini artist. Where can I get data and tutorials for astrophysical simulations?
Okay. So I'll point you at 2 places. One is I know that Blue Waters and NCSA had a Houdini tutorial. Houdini is one of the other 3D software packages I mentioned. So I would check out the Blue Waters website for examples of that. In terms of actual data, whether you're using it in Blender or Maya or Houdini, I would check out my website tutorial, my website of tutorials. That I will put on my screen once we finish the live demo here, and you can download any data from there.
Thanks.
Okay, sure. So let's slide the transform panel off here. And so I'll zoom out with my scroll wheel here. So I now have 4 elements. I have my camera, and I'm right-clicking here, my cube, my lighting element, and my sphere. And up here, I have my overview of my data scene. I'm up here in the upper right-hand corner, where I have my camera, cube, my lighting element called my lamp, and my sphere. So sometimes when I'm building a data visualization, I have certain markers that are for my benefit only, and I don't want to see them in the final rendering. So I can actually click on any of these camera elements, and while they show up in my current 3D viewer, they will not show in the final rendering. If my data visualization scene gets a little bit too cluttered, I can actually turn any of these elements off. They're still present, but they're just not being shown in the viewer. So I click the little eyeball to get rid of them in the viewport. So there goes my cube, there goes my sphere, and I bring it back. So that allows you to that's why it's called the overview panel, and basically show you what's going on and what's present inside your data visualization. Then I have my properties panel, which is on the right-hand side here, and it has a number of tabs. I have my rendering tab, and as you can guess, if I want to render out what something looks like, I can actually do that by hitting the render button. I can also animate it. I can control my resolution in terms of if I want an 1080p HD rendering output, I can change that under the dimensions panel. I can also change what my static output looks like, either with a JPEG or a PNG image, and also what kinds of video compression I'm going to use, whether I want an MPEG or an AVI file. I can control all of that here in the output of the rendering panel. I also have a number of elements including textures, and we'll actually be going over those in the next part of the demo, but also the constraints element. And so what I'm actually going to do here is I'm going to open another file, and we're going to look at a galaxy catalog. And I'm going to stop this here and restart. And we'll open it. There we go. Okay. So this is what my 3-dimensional galaxy catalog actually looks like. And what I've done here is I've I hit on my keyboard the key combination Control-Alt-Q, and this gives me a quad viewport. which shows a top view, a front view, and a view to one side, as well as what the camera is actually showing in the upper right-hand panel. So this is a preview of what the camera is actually going to see. So my camera object is highlighted in orange right now. You can see it. It's very small up here where my mouse pointer is in the top view. But this camera perspective shows what I'm actually going to be seeing in a perspective view. So I can click on my right-hand side here on the properties panel for the camera, and I can select either a perspective, an orthographic, or even a panoramic view. And this is actually very useful for doing the all-sky 360-degree panoramas with the Google Spatial Media module that I mentioned in my slides. I can change the focal length. There are many different presets for popular cameras. So this changes what my data visualization is going to look like in its final output, okay? And in terms of what my objects actually look like, each one of these vertices, I have, how many do I have here? I've got over 7,000 galaxies in this view. The blue square is a grid. We'll talk about that here in a second. But for each of these individual galaxy objects, I don't want to render it as a three-dimensional shaped object with many polygons, because that's going to increase my vertex count, it's going to increase my face count on my polygons, and it's going to increase my rendering time. So what I actually want to do is, under the materials, which is this little spherical tab on the properties panel, I can actually select it to be a halo object. So that really works well for point sources in simulations. I can change the alpha, the transparency of that halo, its size, whether or not it's a hard sphere, and any other properties that are associated with that actual halo. So each point is going to be rendered as a single dot, okay? And in terms of getting the data in, okay, it's already been preloaded here, but Blender has many different GUI views for its interface. So if I go to the top part of the panel, and I'll hover over this here, it says choose screen layout. I can go to scripting, and what this gives me is a single perspective as to what the data actually look like right now, in this case a three-dimensional galaxy catalog, but it gives me my Python script on the left-hand side. So these are all available on the tutorial website that I mentioned, and this is a relatively, this is 50-some lines of code for actually loading in the data. It's relatively straightforward Python code. I have my preamble. I need to do some mathematical operations, and I also want to import the Blender Python environment, so I do import BPY. I've got my data where my simple text file of galaxy locations is actually present. I reset my animation frame, and if I didn't know how to do this, well, I can hover over the animation frame element in Blender, and it will tell me within the BPY module there is an ops class, an animation class, and then finally a class method that tells me how to change the frame. I want to reset it to 1. I read in the data. You can do this any way you want in Python. In this case, I'm using a with clause. Open the data, read it in, read the columns in. In this case, I have the names, the distances, and then X, Y, and Z positions located on a grid, so I read those in from a Python list. And then I go through and I create the objects that are based on a single object template, so I duplicate that single vertex. And then there is a context in the Blender Python module. In this case, it's my actively selective object, so I'm just going to copy it, and I'm going to change the X, Y, and Z position to the list position of 3 elements. I'm going to put a tuple in there of floating point numbers of X, Y, and Z. And once I run this script by hitting the run button, the data are loaded. Okay? Then I can go through and I can texture them with halos. And then I will show you, go back to my default view, what this actually looks like. And if I play the video here.
So while you're playing the video, another question has come up, if you don't mind.
Okay, Okay, another question?
Is it easy to import NetCDF or HDF5 3D data into Blender?
No, because Blender is using Python, so I know there are plenty of HDF5 and NetCDF readers in Python. So if you can read the data in Python and get it into a structure, either lists or NumPy arrays or dictionaries, then you can manipulate it in Blender.
Thanks.
Mm-hmm. Okay, so we'll play that one more time. And I can render this at high resolution. Some of the features that you're seeing there, you see little clumps of galaxies. That's actually the Virgo cluster of galaxies, which is a cluster that is, some 50 million light years away. And this is what we consider the nearby universe. These are all galaxies that are relatively close to our own Milky Way galaxy. So relatively straightforward to bring that into the Blender environment and actually make a three-dimensional rendering of it. So let's go to another example. And I'm going to log back into my machine here. And in this case, we're actually going to be looking at a three-dimensional data cube. So my data import in this case are actually slices of the data cube as two-dimensional images. Each of those images represents a single radio frequency channel. Okay? And I had alluded to, I think in my slides, that your data visualization object elements, what we call our meshes, these polygon shapes like cubes and spheres, can either be physical or they can be used as a data container. Well, that's exactly what I'm going to do in this case. Blender, in its default opening, comes up with a cube as its default object. Well, that's perfect because I actually want to render out a data cube. So what I'm going to do is I'm going to texture that data cube, not with a flat bitmap texture on each side, but as three-dimensional volume elements, volume pixel elements, what we call a voxel. So Blender has this built in. If I go to my Properties tab, which is this little checkerboard tab icon right here, I can actually select the data type as voxel data. And what you're seeing here is a single image from a single slice of that data cube. I change my color ramp, my transfer function, if some of you are familiar with that, to render it out. And then I can actually give it a sequence of PNG or JPEG files, each one representing a different frequency or different channel. And Blender will read in the sequence of those images, and you choose File, Format, Image, Sequence. This is all built in. And it will actually render that. I have 75 frames, so 75 individual channels for my to build my voxel elements. And once that is loaded, since this is a three-dimensional data cube, I want to actually be able to look at it from all sides. So what I'm going to do is right-click and select my camera object, which is now selected in orange. Reminder that I'm looking at my quad view here. That's Control-Alt-Q. And then in the upper right panel, I get what my camera perspective is actually going to look like. Now, what I've done here is actually drawn a curve and then expanded it into kind of a spring-like path such that my camera is going to follow that track but always be pointed at the data cube, okay? And so if I hit my play button down here on my animation bar, you'll see the camera moving, but in the lower panel, you'll see it slowly rising up, all the while constantly being focused and pointed at the data cube. And as you'll see in this example, this is actually a data cube of hydrogen cyanide that was taken with the ALMA telescope, the high-frequency radio telescope in Chile that I mentioned. And we can actually see the separation of two elements that were in the core of the comet. And I also have labels for the coordinates on all three sides of the data cube. And it's reaching the end here as it comes back to the beginning, and it starts over again. So I can drag this green line at the bottom to go to any time step of my data visualization. And if I go to the camera, which is selected here, right-clicking and selecting it, it's highlighted in orange right there, and then go to this little chain icon in the Properties panel, these are my object constraints. So I have two different constraints here for my camera. The first one is I want to follow a path. Okay, it's this curve right here that I've drawn on the screen. But even though I'm following that path, I don't want the camera pointed in a single direction, either X, Y, or Z. I always want to be pointed at the data cube. So I can click and say, add an object constraint. And you see there's lots of different kinds of constraints that you can put on objects. You can clamp it onto something, you can lock it, you can follow something, you can follow a path, you can pivot around something, you can make it a child object of something else. But in this case, I actually want to track to, and then I select, okay, well, what target do I actually want to look at? And in this case, it's my named data cube. Okay, so that allows me to view the data visualization in 3D, and as my video plays, I'll actually see what it looks like. So I'm going to show you two examples of this rendering output. The first one is a comet. So what you're going to see here, if I can make this full screen, this is the rendered output of the Blender session that we just looked at. And you'll see there are roughly two elements in the middle, kind of a northern and a southern component. So this is not a three-dimensional model of the comet itself, but of the dynamics of the chemical element that we're actually looking at, in this case, hydrogen cyanide. So we'll play that again. So without looking at this data in 3D, if we just played this as a static movie, moving through the different frequency channels, we would see blobs appear and then disappear on the movie of the data cube. But actually rendering it in 3D allows us to see this breakdown of the two different components. So this was taken by some of the scientists here in our building, as well as some of their collaborators at NASA. Very, very nice project done with the ALMA telescope. So let's go to another example here. This is a circumstellar disk. Again, this is mapping the dynamics of said disk with the ALMA telescope in 3 dimensions. So you see not only the streams coming out of the disk, but the rotating motion of the material that is around the disk. And if you know anything about rigid body dynamics, those are going to be tilted at 45 degrees, and you're going to see an opening if you map that out in its position on the sky, but also with its Doppler shifted frequency. So this is what this data cube looks like in 3D. This was from a very nice Nature paper with some early results from the ALMA telescope in Chile. Okay. Another example that I would like to show are n-body simulations. Okay, so in the similar fashion of actually reading in a catalog or any type of XYZ position data from an ASCII text file. Let me make this full screen. And this shows 2 Milky Way sized galaxies colliding. Gravitation takes over. The galaxies are disturbed. They make another near pass to each other, and eventually coalesce to form a single object. But as I'm doing the visualization, I'm not only letting the animation play out from each of the subsequent snapshots that were done in the simulation, but I'm moving my camera around at the same time. And then finally, I'd like to look at another example, if I can switch viewers here. This is a simulation done by one of my colleagues, Matt Wood at Texas A&M University in Commerce, of a cataclysmic variable star. So this is a binary star where material is coming off of one element, one star, into another. And the curve that you see here is actually the zero velocity curve. And if I can rotate those in 3 dimensions in Blender, I can create a surface of revolution and actually let the simulation play out. So you're going to see, if I can go back to the beginning here, where everything is lined up and play, you'll see the simulation play out. And you'll see the particles circling around, but they don't go out the boundary, outside the boundaries of the zero velocity surface. And the reason I'm showing this example is because I want to point out something here on the bottom of my animation. What I'm using here are animation elements called keyframes. Okay, so each of these yellow marks shows a specific view during the animation. In this case, I'm moving my camera, that you see, I'll highlight it in orange with my right mouse button, is moving very, very, very slowly. There are actually several elements that are moving. One, the Roche lobes, okay, indicated by this curve right here, are actually moving around. I also have the simulation playing, okay, right there now highlighted in orange, and there are lots of keyframes for that because the simulation has to play out for the entire video. And then I have a couple of keyframes for my camera, which is going to be panning very, very slowly during the course of the simulation. So I've got multiple elements all moving here together. So let's go back to our example with our cube, and I'll show you how to actually insert those keyframes for an animation. I'll start a new file, and I'll start a new session here.
We have another question after you do that.
Yeah, please go ahead while I get things restarted here.
Does Blender have a native understanding of MKS units, or does it have to be taught?
No, it does have an understanding of MKS units. And I can actually show that, I think, over here on the right-hand side. There transform orientations. There is a display. There is actually an option in one of the menus here to actually change the units, whether you want to do meters or kilometers, but it does natively understand MKS units. So if you're building some sort of physical simulation where distances have to actually represent something physical, then yes, it does understand that. So for everything that I've been showing you, with either a n-body simulation of galaxies colliding or the galaxy catalogs, the grid that I'm laying out, and I'll show you how to do that here in just a second, actually has a physical representation. In my case, it's usually something like 20,000 light years, or we use measurements called parsecs. It actually has a physical association, physical meaning to it. So yeah, so we'll do our keyframes here, and then I will show you actually how to set up a grid within your data visualization. So if I want to actually move an object or camera or lighting element, I can actually place that object with my G key. Let me turn on my screencasting here. So move it with my G key. And then all I want to do is I want to move the cube from the left-hand side of the screen to the right-hand side of the screen. So I'm currently frame 0. I'm looking at the bottom of my screen. My start frame is 1. My end frame is 250. I'm going to do 30 frames per second, so I'm going to increase this to 600 frames. Then I'm going to keyframe by hitting the I key. And this little drop-down menu comes down where I can change the location, the rotation, the scaling. I can do any combination of those, or I can do all three with location, rotation, scale. And what that does is it will signify with a little yellow bar in my animation timeline the position and all the properties associated with said object. So I will click location, rotation, scale, and now for that frame it is locked. Now I'm doing 30 frames per second, so let me move to frame number 60. So 2 seconds later, I want my cube to be at a different location. So I hit the G key, I move it somewhere else, and I again hit the I key. I keyframe it with location, rotation, and scale. In fact, I'm going to scale it, make it a little bit bigger, and I'm going to rotate it with the R key. If you're following the lower left-hand side of the screen, you can see what I'm doing. So I'm going to rotate it. Now I'm going to hit the I key and insert a keyframe, locking the location, the rotation, and the scale. And now I'm going to go back to the first frame, and I'll hit my play button. And it will translate, it will rotate, and it will scale between those two frames, or between those two keyframes, I should say. Okay, so that's how you move anything. And if I wanted to know how to change the location, the rotation, and the scaling, well, I did that in one of my earlier scripts, and I can just hover my mouse element over any of these elements. And note that if I go back to a frame, in this case frame 1 or frame 60 that is keyframed, the location, the rotation, and the scale in Blender have now been highlighted in yellow, saying that those positions and those properties of said object, in this case a mesh cube, are locked in that keyframe. Okay, so that's how you actually insert a keyframe, and you can do this in the Python script by just hovering over, and this tells me that bpy.data.objects, in this case cube, has a property in that Python object called location, and I can change that to whatever position I want. And that's how I'm building my simulations or my catalogs. In the case of doing n-body or spherical hydrodynamic simulations, or when I was showing you the cataclysmic variable star, each one of those positions is going to be keyframed at every single frame because I have a different snapshot at every frame. But because I have a Blender Python API, I can easily script that into Python just like I would be in making any kind of graph with Python. So somebody asked about MKS units and a grid. So let's go back to the galaxy example. Okay, and I had mentioned that this blue object in the background here is actually a grid. And we talked a little bit about lighting elements, and there are, your physical lighting elements which are illuminating physical things in your data visualization, but sometimes you want an object to actually illuminate by itself. So if I click on this blue object, which is just called plane because it's a planar object with four vertices associated with it. Well, it starts with 4 vertices, and I go to this material tab, which is this little sphere on the right-hand side. I have surface shading, I have volume shading, which we used for our data cube. I have halo shading, which I'm using for my galaxies in this galaxy catalog, but I also have a wire shading, okay? So if I click on wire and change the intensity to a certain value and color, if I go back to my slides, this grid that you see in the background of my 3-dimensional galaxy catalog is actually a wire mesh element. So that allows me to give a reference view in the background for something like rendering a 3-dimensional catalog, or if you're doing GIS and you've got maps that you want to import, you can lay down a grid like that, and it gives your viewer watching your data visualization a reference frame in the background to actually say, okay, well, these grid squares, in my case here, are X number thousands of light years in size, and that way they know the scale at which you're actually looking. So that's a great question. Okay, so I've shown you an extragalactic catalog and how to import your data with Python. I've shown you an n-body simulation. I've shown you a data cube, and I've shown you surfaces of resolutions, surface of resolution with a cataclysmic variable star, and that covers kind of a variety of different kind of astrophysical phenomena that you can actually import and visualize with Blender. So I'll return to my final slide here and put this up. I actually have a book called 3D Scientific Visualization with Blender that's published through Morgan and Claypool and IOP Science. There's a companion website that you can see here on the first link that has PDF tutorials and short video tutorials about how to do some of the things that we've talked about today. I also have a YouTube channel, Twitter and Instagram on social media called Visualize Astronomy. So check out some of the videos right there. You can go to my website and I get my email and any of these social media contacts. And I'm giving this tutorial at the invitation of my colleagues at NCSA. And my hope is that people watching will get ideas and be inspired to do some of their own scientific visualizations with Blender. And I'm always happy to collaborate and work with people not only in astronomy but in other fields to accomplish this. So I look forward to hearing from some of our viewers about some of the ideas that they would like to have. And again, thank you to my host today at NCSA. And I'll finish there. And if there are any questions, I'm happy to take them from our moderators at this time. And thank you very much for listening.
Thank you, Brian. So we had quite a few questions from YouTube, but
Okay.
I would like to ask actually a couple of my own questions.
Sure.
So the first one, you mentioned a few domain-specific modules for Blender. So the question is there a place where people can find these modules, or do they have to search the internet? And is there some sort of a community built around scientific visualization with Blender?
So I think one of the best sources is the Blender forums, which you can get to from the main Blender website. I also have a collection of links on my website pointing at different resources in different areas that you can explore, not only with the things that I've talked about today, but actually getting started with Blender, because obviously there's I think it's very fun software to use, but there's a little bit of a learning curve. I think that anybody who works with scientific software will be able to pick up very quickly. And I would also point out one of my colleagues, Jill Naiman here, has a package called AstroBlend that people should check out as well. So I think the Blender forums, Jill's website, or my website are the places to start. And I believe I've listed my website in the YouTube chat window, so people can start there.
All right, thank you very much. Actually, Jill is in our YouTube live chat. So my second question is, some of the objects or phenomena are very difficult to visualize. For example, things like black holes, tornadoes, electron clouds. Have you ever stumbled upon such a problem when you were working with Blender, and how did you solve that?
Right. So I showed the example of the curve of zero velocity for the Roche lobes in doing the cataclysmic variable star simulations. I didn't actually do the simulation. The data was given to me to actually visualize, and my colleague wanted to move the camera around as the simulation played, but they wanted the Roche lobes to be visible during the entire simulation, but actually see inside of them. And so one of the things that you can actually do after you build a surface of revolution is you can actually change the transparency of that. So I think with some of the examples that you mentioned from one of our listeners, being able to tweak the alpha value and the transparency to actually be able to look through things is advantageous when you're actually doing your simulation. Otherwise, you either can't see through something, or your data visualization becomes too cluttered. So I would take a look at some of those elements, and I have examples on my website of how to build some of those things.
Thank you. And my final question. So you are a scientist, and without a doubt, visualization is very important for science. But in the end, you have to spend time on actually visualizing things. Why do you think scientists should visualize data themselves, and when should they reach out to professionals?
So our question is when should scientists reach out to professionals? I think when they get to the point of having their data visualization taking too long to render, or bogging down their workstation hardware, I think that they probably have in their mind what they want to do, and maybe they have their data, for example, imported into Blender, but they need to be a little bit more creative and efficient in how they're actually doing their rendering. So the conference that I had mentioned, SIGGRAPH, Special Interest Group for Graphics, is wonderful for that, because those people will understand where you're coming from, but might immediately see, okay, you can increase the efficiency of your data visualization in said manner, because they might not be working on your specific scientific application, but their data may be similar to what yours actually what yours is, and might be able to help you out with those data visualization struggling points, if you will. So,
all right, thank you very much. We have one more question from YouTube.
Okay.
Let Scott ask.
So one of our viewers waves hi and asks, are there new features in Blender that you're looking forward to? For example, anything new with the volume renderer, or cycle-specific things, or other?
Yes, so Blender has a new, I think I mentioned briefly in my slides, a beta version of 2.8, which has a new rendering engine associated with it. And I'm really excited to use this. So they will have their default, their cycles, and then the new rendering engine, which is still under beta test out. And I'm really looking forward to trying that and see how it works, especially with the volume rendering. So stay tuned. You can go to blender.org today, and you can download the beta and give it a shot. They have, I think the Blender interface is relatively intuitive, and they have made significant improvements over the past years leading up to this new 2.8 beta. So definitely check that out. But I'm looking forward to the new rendering engine.
Thank you very much, Brian. So we don't have questions at this moment, so let's maybe cut here.
Okay.
So first of all, thank you once again for providing this wonderful webinar. I'd like to remind everyone that our next webinar will be on March 20th, and it will be on SnakeMake. Once again, feel free to ask questions on our Slack channel. We will relay them to Brian whenever you ask them. And I'd like to thank you all for joining us today, and I'll see you in the next webinar.